the previous video, we actually talked about there's a matrix and we have the resins all over here. Sorry, not resins, the fiber reinforcement. Sorry. So the matrix, just to recap, is that the matrix itself, in engineering term, they are called matrix. But for the commercial term, or in the commercial world, they call the matrix, they call it the resin. Okay, just a recap. Anyway, so yeah, so therefore, if you were to pull in this direction, this is called the fiber. I mean, this is called the longitudinal E1 Young modulus of your composite, and over here this is a transverse E2, right? Your Young modulus in the two direction, all right. And this is for the Rails model. Sorry, this is this is E1 is the Voyage model, the E2 is the Rhodes model, all right. And therefore now we're going to talk about the interactions between the E1 and the E2, okay, which is considering the shearing. Alright, we call this the in-plane shearing, as being suggested over here, in-plane shearing force. So you're looking now at the top view, okay. So if I have this thing over here, alright, I'm looking at this side. So I'm actually looking downwards in this picture, okay. So if you have a shearing, this whole thing we're gonna shear. So at first it was like this. Now after you shear, it may be something like this. Or maybe I should, you give me a while. Yeah. So this is the in-plane shearing, where overall your whole thing we're gonna shear in this manner. Okay. So as you can see, your whole cube is being sheared into this shape. Okay. Hopefully it's pretty clear now. Okay, so you are shearing with this particular angle, alright, some angle phi, which is being attributed over here, alright. So instead of the normal stress that we often write and the normal strain that we often write, alright, so currently now we call the stress as tau. Shear stress is called tau, and the shear strain we call gamma, okay. And therefore the formula for the Hooke's law, for example, this is the Hooke's law, stress is equals to Young modulus times strain, alright. For the shearing, the tau is equals to the shear modulus times the strain, the shear strain, alright. So this is the shear stress, this is the shear strain, the same thing all over here, and which is why it's being represented over here, alright. There will be a G12. G12 means that you are interacting with the one direction. This is the longitudinal direction 1, alright, and the 2 direction, alright. Remember, just now in this picture we have E1 and E2, so the 1 is in the 1 direction, the 2 is in the 2 direction. Hopefully this is pretty clear. So this part we have understood, alright. It's just the Hooke's law in terms of the shearing, alright, shear Hooke's law or whatever thing that is, but it's the same thing. Okay, now we talk about the shear strain, the gamma. Okay, previously in the strain, alright, this is the strain where in our, we say that this is a bar and you have a certain strain, this is some changes of length with divided by its own length. So the strain is changes of length divided by length, original length, alright, it's just this equation. As for the shear strain, alright, there is no original length, but rather than there is only one length that is often the same, which is this length, alright. As you can see, this is x0, okay. So your x0 is always the same, okay, while your this thing is changing, alright. As for example, if you have like this thing over here is always the same, alright. And as you switch a certain angle, alright, this side is going to increase, alright. And as you go furthermore, this length will be going to increase. So this is changing. So we utilize the same analogy that for you to memorize easier, such that it is something like this, changing of the length, okay, or changes the anyway, yeah, let's write like that, okay. It's the same thing as this, okay. And based on the Pythagoras theorem, you have an angle over here, this is O, this is A, alright, the Torcasio thing, alright, tangent, cosine stuff, alright. And therefore, most probably if you think about it, this is your O, your changes in the length, alright. If I will draw a triangle like this, alright, this will be clearer. So this is your O, your changes in length, and over here this is your x0, alright. So it's O, the opposite divided by adjacent, so it's opposite divided by adjacent, and therefore most probably you would know that this is actually a tangent. Alright, so you are tangenting or tangent or whatever tangent your angle over here. Alright, so you're trying to tangent this angle, alright, because of the opposite over adjacent phenomenon that is occurring over here. Since your angles is changing, the O will change. Alright, so I repeat again, when your angle, this angle is changing, alright, this one will change. So this is why we're using tangent, okay, so to speak. Anyway, so at least you get to understand this thing. Alright, and the angle itself is just the angle of shear. Okay, these are all the definitions. And same as for other two videos very early ago, we are actually finding the Young modulus of the composite. Alright, in terms of the one direction or the two direction. Alright, in this case we are also finding the shear modulus. Alright, instead of Young modulus we're talking about shear modulus. Okay, which is the G. Okay, and therefore in this case let's see how it goes. Alright, actually it took quite a while for me to understand this whole thing. Alright, and I'll just start off with this thing first. Okay, instead of going through the step-by-step thing. Okay, the overall changes, alright, the overall changes over here is determined by the overall changes of the matrix. So after you shear, the matrix will be sheared in this manner. You have to know what is this matrix over here. The matrix of the changes of the matrix. Alright, and you also want to know the changes of the fiber. Okay, and therefore they add up together, they will give you the overall changes in the whole the triangle thing. Okay, so with this understanding, how can we expand things? We know that the shear strain is the gamma equals to the changes, which is this one, divided by the x naught, which is what I've said just now. This is x naught. Alright, now they say it's w, but later on we'll see why. Okay, but anyway, it's over here. Okay, and I'll just simply rearrange, and I have this equation where I bring this upwards. Alright, so x naught times gamma equals to this one. Okay, I think this is pretty clear for you. And therefore, since we know that the triangle can be represented by this thing, alright, and therefore I can just simply sub in. Alright, so this thing, alright, if it's gamma, then I just sub in as x naught gamma, alright, is equals to now it's triangle M, so I'll just write as x naught matrix gamma M, then plus x naught the fiber, and then gamma, the fiber. Okay, and if you were to compare, the x naught is always the same, and it makes sense because the x naught doesn't change at all. It's just the thickness of, it's just the length or the breadth of the thing, because this is your plane. After you shear, alright, is this thing changes, but this length over here is still the same as I've said just now, and therefore let me edit a little bit. Alright, so forget what I've just written over here. Okay, I'll just rewrite answer in front of you, because since the x naught is the same for all of this side, alright, for the matrix or the fiber, the x naught is always the same. Then I'll just simply make them the same, x naught. So they are the same, they are all the constants for x naught. Okay, and because they are in terms of fraction, this thing plus this thing equals to certain amount of composite. Alright, so this strain is the overall composite strain. Okay, hopefully you get what I mean. So initially this is the first step. Alright, I hope that you understand the changes in the matrix, or which is this one, and then the changes in the fiber will give you this equation. Next, knowing this shear strain equation, I rearrange, I bring this thing up, I'll have this thing over here. Okay, next I sub in this equation, alright, this triangle as this one, alright, into here, each of them. Okay, and therefore I would have this thing. Alright, knowing that the x naught doesn't change at all, so I keep it there. Alright, the only thing changes is the gamma, the shear strain, and the changes in the strain. Alright, or changes in this platform over here. Alright, and now this is something plus something equals to something. Alright, and this makes the sense that maybe a certain percentage amount plus a certain percentage amount will give you the full 100% of the composite, right? Because the fiber plus the matrix will give you the full composite, and therefore in this case we'll require a ratio. Alright, and this is where the ratio comes in. Alright, so if I take a while, I'll have a volume ratio, alright, VM, alright, and I'll have a fiber volume ratio of the fiber, VF, okay, and this ratio, this VM and this VF are not in meter cube or cm cube or whatever. They are just ratio, so this means that there is no unit at all. This is just a simple ratio ensuring that this thing is equals to 1. So we set this as equals to 1. Alright, in order to have that to be equals to 1, we will require a certain ratio also, and this is why this VM and this VF come in. So comparatively to the conventional one that we have just done in the earlier videos, our VF and our V often comes about taking you see, for example, taking area times length, you get your volume. Alright, so in this case we didn't actually do much about that theory. We just straight away sub in the ratio and that's all. Okay, and I also don't know how come, but anyway, you can just take note of this is why the step comes in. Alright, it's just simply to get the ratio and you somewhat get the meaning of things. Alright, okay, so I think I've rewritten the things in terms of what we have just said earlier, or at least it's easier for you to see. Alright, this is the changes in the M plus changes of the F, which is the picture over here. Okay, I know I keep on repeating, but at least hopefully it will make things clear. And after that, I rearrange the shear strain and sub it in over here, and this is what we have, right, in terms of the volume ratio, ensuring that, or knowing that this is equals to 1. So this is some ratio and this is some ratio. Okay, the next thing that we will require in this understanding is this. Is the shear stress is equals to the shear modulus times the shear strain. Alright, and since we are writing in terms of the shear strain, alright, and our objective is to find the modulus of the shear system. Alright, what we can do is to bring this gamma down, okay, or perhaps I should bring this G down. Okay, if I were to bring this G down, I would have tau divided by G is equals to gamma. If you don't understand what the hell is this is very similar to your stress is equals to Young modulus times your strain. Okay, this is the Hooke's law. Alright, this is very, I think you remember already. So this is analogous to your shear stress. This is normal stress, this is the shear stress. Okay, hope that this is pretty clear. And therefore, you can just simply sub in your gamma as tau over your shear modulus. Alright, so this gamma over here, I will just sub in individually as their own systems. And before I go into that, I'll just change this gamma. Instead of the shear strain of the composite, to be more clear, I should write in terms of shear strain of the plane 1, 2. Alright, so this is the fiber that you arrange. You pull in this direction is called 1 direction. You pull here is the 2 direction. Alright, so the shearing is in terms of the 1, 2 direction. Alright, because you are pulling in the 1 and 2 direction. I think you get what I mean. So I'm shearing in the plane of this direction and this direction. Okay, hopefully you understand what I mean. It's just shearing in the 1, 2 direction. It raises the next question, that is this G21 or G12? Okay, you may say never mind lah, same, but think about it. Alright, if it's 1, 2, you're talking about plane 1. Alright, this over here is plane 1. Alright, in the 1 direction. So if you are pulling in plane 1 in the 2 direction, you're actually moving in this direction. You're actually moving the plane 1 to the 2 direction. So it sounds not very logical, right? So you are somewhat trying to say that it's shearing in this manner. Alright. However, we are in fact not shearing in this direction. We are shearing in this direction. So if that's the case, then this means that we are actually shearing in plane 2 in the 1 direction. So it's something like this. So this should be G21, not G12. Right? So I'll leave you to think about it. But at least this is something to be considered, I guess. Let's just follow the book, because the book should be correct. But it just raises the question of why is that like that. Or maybe my understanding may be wrong. But anyway, let's continue. So we have just successfully sub in the gamma as this thing, which is all along this one, right? The shear stress is equals to the shear modulus times shear strain. Alright, then we rearrange to bring the G down in terms of gamma, and then subbing gamma as tau over G, okay, and you have all this thing coming out. Alright, and the next thing that we come and go is to cancel off. Cancel off what? Cancel off the common term. This x0, and x0 over here, they are the same common terms. Maybe I should use different color. Yeah, these things, they are the same common term, x0, because this thing, or in other words, this thing, this x0, and this thing is your, and this thing over here is your changes of 1, 2. Alright, so therefore, alright, yeah, so when your angle is bigger, alright, this length will change, alright, but this thing over here will never be changed, alright, and this is something that is constant throughout every of the fibers and the thing, alright. And the next thing you may also ask is that if that's the case, then if it's x0, this whole thing is x0, then this should be maybe half of x0. This should be half of x0. Why do we use the full x0 and as a constant for all of them? And I also don't know why. And I think mathematically, both of this thing will eventually give you the same answer. This is why they make it in the sense that x0 is the constant throughout all the fibers and the matrix. As you can see, for the matrix, this length isn't x0 at all. You see, and this length over here isn't x0 also. This is some portion of x0. Alright, but I think mathematically, if you were to add them up together, it should come back to equals to this form. Okay, and this is why they use the constants at x0. So these are all the math that it involves that you would want to understand when you in the future that you may need this understanding, just to put it here. Anyway, so next is your stress. Your shear stress is the same. Alright, it's the same throughout everything. And I will assume that this is an assumption that the shear stress are all the same throughout all the matrix and the fibers to keep things simple. Alright, but nonetheless, these are the stuff that are constant. So if I were to cancel them all together, what I will have are this. Yep. So this thing, if you were to cancel, you're only left with this and this. Alright, same thing over only left this and this also. Okay, and this is exactly the same as this form. Okay, if you think that I cheat or feeling, this thing is the same as this thing is the same as this. Alright, same thing. Alright, and this is how you find your shear modulus. Alright, nonetheless, if you can rearrange, alright, you would have, oh mind, I'll just leave it like that lah. Okay, so after you calculate your this thing, and then you take your answer divided by, okay, maybe I should rearrange this stuff. So what I have is equals to G12. So I bring this whole chunk into the denominator, I bring this out to the numerator. Okay, so what I will have is this form. Okay, and if you find this a bit more chim, then I can simply also rearrange this stuff to make things easier for you to see. Okay, so I'll just simply multiply. Maybe I should use a different color and a different size. So I will have a GMGF divided by GMGF. Okay, so this is the equation that you will see. I mean, this is the equation that I use to make things simple. So this is equals to 1. So I'm just simply rearranging the stuff only. Alright, so what I would have is GMGF, which is this one, multiplied by 1. Okay, and this thing over here, this GM will cancel out with this GM because this is numerator, this is denominator. So all I will have is VM times GF. Okay, this is just pure math now. Okay, and then plus, alright, this GF will cancel out with this GF, while this GM will retain and multiply with VF. Okay, so I will have VF GF. Okay, sorry, VF GM. Okay, and this is equals to G12. Okay, and this is the shear modulus equation to get a shear modulus lah. Okay, so this is for shearing. Alright, and if you want to make things more simple, because if you still remember VM, alright, VM is in terms of 1 minus VF. This is something that we see in the previous videos already. Why is because V and the volume fraction of the matrix plus the volume fraction of the fiber is equals to 1. Alright, so maybe this is 90%, this is 10%, equals to 100%. So this is something like 0. So this is like 0.9 plus 0.1 is equals to 1. Same thing lah. Okay, so to keep things more simplified in terms of your VF, okay, then I will just write down a new one. I will change this VM as 1 minus VF. Okay, and this is it, your full equation for your shear modulus. Alright, and yeah.